Hello viewers. Welcome to the YouTube channel. In this video we will study about class 12 or 2nd PUC Physics Chapter 1, that is Electric Charges and Fields, class 6. From basic to advanced level. So watch till end, share, comment and subscribe the channel. In the previous class we discussed about the following topics, they are: physical significance of dipoles, expression for the torque, couple, acting on an electric dipole placed in a uniform electric field, continuous charge distribution, linear charge density, surface charge density, volume charge density, Gauss's law, significance of Gauss law. This video link is given in description. Don't miss it. Support, share and subscribe. Now, we look into applications of Gauss law. Let's start. Applications of Gauss law. Using Gauss law. 1. Electric field due to infinite long straight uniformly charged wire can be found. 2. Electric field due to uniformly charged infinite sheet can be found. 3. Electric field due to a charged thin spherical shell can be found. Let's see one by one. 1. Derive an expression for electric field due to infinitely long straight uniformly charged wire using Gauss law. Solution. Consider an infinitely long straight charged wire. Let lambda is equal to linear charge density of wire. E is electric field at a point P. R is distance between wire and P. Draw a cylindrical Gaussian surface of radius r passing through point P as shown in figure. Let Q be the charge enclosed by the Gaussian cylinder. The electric field is radially outward. That is, perpendicular to wire. Therefore, flux through the end faces is 0. Because there are no components of electric field along the normal to the end faces. Therefore, phi is equal to E into area of curved surface. That is, phi is equal to E into 2 pi RL. Mark as equation 1. From Gauss's theorem, phi is equal to Q by epsilon naught. Mark as equation 2. But lambda is equal to charge by length. That is equal to Q by L. On equating, Q is equal to lambda L. Substitute in equation 2. We get phi is equal to lambda L by epsilon naught. Mark as equation 3. On comparing equation 1 and 3, we get E into 2 pi RL is equal to lambda L by epsilon naught. Therefore, E is equal to lambda L by 2 pi RL epsilon naught. On cancelling L from numerator and denominator, we get E is equal to 1 by 2 pi R into lambda by epsilon naught. Or, E is equal to lambda by 2 pi R epsilon naught. This is the expression for electric field due to a charged long wire. 2. Derive an expression for electric field due to a uniformly charged infinite plane sheet. From figure, E is electric field on either side of the sheet. R is distance between the sheet and each end face of cylinder. Let A is area of each end faces of Gaussian cylinder surface. Q is charge enclosed by the Gaussian cylinder surface. Sigma is surface charge density on sheet. The electric field lines are parallel to the curved surface of the Gaussian cylinder. Therefore, the electric flux through the curved surface is 0. The electric flux through the Gaussian cylindrical surface is Phi is equal to flux through end phase 1 plus flux through end phase 2. That is, phi is equal to E into A plus E into A. Because phi is equal to E into area, which is equal to 2EA. Mark as equation 1. From Gauss's law, phi is equal to Q by epsilon naught. Equation 2. But sigma is equal to Q by A, which gives Q is equal to sigma into A. Therefore, equation 2 becomes phi is equal to sigma A by epsilon naught. Equation number 3. On comparing equation 1 and 3, we get 2EA is equal to sigma A by epsilon naught. Therefore, E is equal to sigma by 2 epsilon naught. This is the expression for electric field due to plane sheet. Note 1. In vector form, vector E is equal to sigma by 2 epsilon naught n cap, where n cap is unit vector. 2. E is directed outward if sigma is positive, that is Q is positive, and E is directed inward if sigma is negative, that is Q is negative. 3. E is independent of distance from plane sheet. Next, application 3. Derive an expression for electric field due to a charged thin spherical shell using Gauss law. Case 1. Electric field outside the shell. Consider a charged thin spherical shell. Let R is radius of spherical shell of center O. E is electric field at a point P. Q is charge on spherical shell. Sigma is surface charge density. Delta S is area element around the point P. P is point at distance R from O. The electric flux through the Gaussian surface is given by phi is equal to summation of E into delta S cos theta. Equation number 1. The angle theta between E and delta S is 0 degree, then cos 0 degree is equal to 1. From 1, phi is equal to summation of E into delta S. Equation number 2. Where area of Gaussian surface, summation of delta S is equal to 4 pi r square. Substitute in equation 2. We get phi is equal to E into 4 pi r square. Equation number 3. From Gauss's law, phi is equal to Q by epsilon naught. Equation number 4. On comparing equations 3 and 4, we get E into 4 pi r square is equal to Q by epsilon naught. That is equal to E is equal to 1 by 4 pi epsilon naught into Q by r square. Or E is equal to sigma r square by r square epsilon naught. Because Q is equal to sigma into 4 pi r square. This is the expression for electric field at a point P. Case 2. Electric field inside the shell. Consider a point P inside the spherical shell. Consider a Gaussian surface passing through point P as shown in figure. Electric flux through the Gaussian surface is phi is equal to E into 4 pi r square. Equation 1. According to Gauss law, phi is equal to Q by epsilon naught. Equation 2. From equation 1 and 2, E into 4 pi r square is equal to Q by epsilon naught. Charge enclosed by Gaussian surface. That is Q is equal to 0. No charge is present inside the shell. Therefore, E is equal to 0. That is, Electric field due to a uniformly charged thin spherical shell is 0 at all points inside the shell. This ends Chapter 1 all theory topics. Don't forget to share, subscribe the channel for more updates.